Okay, we have started the recording, Chethan. Welcome again. Let's start your seminar.
Okay. So, so I'm going to talk about some recent stuff that I have been doing in relation to this information paradox stuff. So, and the talk is basically going to be based, can you see the cursor, by the way?
Yes, we can see it, yeah.
Okay. So, so the talk is basically about this 2007 paper from this month. But it's also like, so there are two approaches to this, as you will see. There is this doubly holographic approach, and there is like this not so doubly holographic approach. And so I'm going to talk about the doubly holographic part. And there was some work that I did with some very good undergraduate students, especially Jude, who was kind of stuck between, you know, he was a master's student at Cambridge, and now he is stuck here in Corona season. So and he's applying right in this year. So yeah, so let me start by giving a general introduction to information paradox. I won't talk about all the aspects of it because there is too many. So I'll just say a few things about the kind of things that will kind of be relevant for my stuff. So so what I'll call that the weak information paradox. And there are many questions of increasing subtlety which go by the name of information paradox. And the basic one that one could, so the original version of it was Hawking's original version is the statement that when a black hole evaporates, you end up losing information because, you know, so the radiation is thermal and so on. So this problem is basically solved if AdS-CFT is true. And it has to be solved in some way, because of the fact that AdS we expect that is dual to a unitary theory, and so this effect in some sense is a large n is equal to infinity type of effect, and the finite n you expect the theory to be unitary, and you don't you think that you know, you would expect that the theory has some unitary resolution to the information paradox that Hawking started. So let me also say that at any point feel free to interrupt. So because I cannot see you, it just looks kind of like I'm talking into the air, so to speak. So yeah, so but the reason why AdS-CFT is it's not considered to be a complete solution to the problem is because Hawking's semi-classical calculation, where exactly does it go wrong, is not clarified by AdS-CFT. So, and this is because implicit in you know, in part of Hawking's semi-classical calculation is the picture that black hole is localized in the bulk as a subsystem of the entire geometry. So, and that is kind of implicitly needed in order for you to do this quantum field theory in curved space type of calculation that Hawking does in the background of the black hole. So this is a difficult thing for in AdS-CFT to manage, because bulk locality. So if you have a subsystem that is localized somewhere in the bulk, it's not easy to ask such questions in holography, because truly diff invariant observables are integrals over all of bulk, and therefore have support only at the boundary. So yeah, so the truly microscopic degrees of freedom, the truly CFT degrees of freedom do not even directly see, it's not clear how exactly they see Hawking's calculation. Okay, so, so one thing one can do is to elevate Hawking's implicit assumption that black holes are localized objects into an explicit assumption. So one thing, you know, so one of the ways in which you can make this problem a little bit more concrete is to make this into an explicit assumption rather than an implicit one. And what that means effectively is that you split the Hilbert space into two. You assume that the Hilbert space can be split into two approximate tensor factors, and imagine that the black hole is living in one. So one of them, and then the radiation
Chethan,
is.
can I ask a question?
Yeah, sure, absolutely.
It is like more basic, in the sense that in this AdS-CFT correspondence, there's no observer or anything, right?
Yeah.
And that is one thing. And general AdS-CFT correspondence, we don't have a horizon unless we put a black hole, etc.
Right. So
where is the observer dependence coming in the AdS-CFT story?
That's in my title. The reason why I put this weak information paradox is because, as I said, there are various questions of observation and how exactly you can reproduce, you know, the original state, and what can you say about the interior of the black hole. There are various questions like that. So the reason why I put the weak information paradox is because I'm kind of trying to look at it in some sense, the you know, so the current developments, so to speak, address in the most basic issue, which is that you have to see the page curve. That's what you're trying to see. So you're not like trying to understand how exactly you might be able to decode the Hawking radiation that comes out of the black hole. I mean, that's obviously a next step.
No,
But
because
at the
there are
moment,
people who argue that the page curve is a wrong computation. It's a correct but wrong computation, which has no relevance. You know.
So I think they are wrong. So,
Okay.
so
Okay,
the point is that, so I think that there is a sense in which, so the basic argument is, very roughly speaking, that at least in flat space, or for instance, a small black hole in AdS, so what you expect is that for a sufficiently, if the curvature of the black hole is sufficiently small, then you expect that the Hawking radiation throughout its evolution is escaping, there is the effective field theory should be a well-defined description of the place where the radiation is exiting the black hole region. So I think that needs to have an understanding in some sense. I mean, maybe the page curve calculation is somehow there has to be an understanding of it, which is something else. But I'm saying that this particular fact needs an understanding. Otherwise, you're not solved the real information paradox. So, or at least the one version of the information paradox. So here, what we are going to do is, what people have tried to do is just the fact that, so how exactly, so there is a detail, so you will see in a couple of slides what exactly constitutes a so-called, a semi-resolution of a particular aspect of the information paradox, but even that is not quite complete, I would say. So,
Chethan,
yeah.
So would you agree that although it might be hard to define the black hole interior in this via CFT, at least the radiation, like a Hawking radiation, should be kind of, it's easy to define, like any gravitational radiation, for example. Some kind of one should be able to actually isolate
the question
the
of relating bulk effective field theory with the CFT fine grained degrees of freedom is a complicated question, I think. So bulk effective field theory. So essentially, what we mean by bulk effective field theory, if it is a black hole, is that you have a semi-classical state, which is let's say some large black hole. It has some description in terms of some CFT state. And then there are fluctuations on top of it or something like that, which you imagine to be a description of bulk effective field theory. So the degrees of freedom, and I think that asymptotically, they might have better and better descriptions, close to the asymptotic boundary. But I think the question of how exactly one can reconstruct the full information about it, I think that it is, well, I mean, it's basically, it is still, so yeah, I don't have anything to say about it. Let me put it that way.
Okay.
So what
I was thinking at least the entanglement wedge is a very well-defined observable to actually define the radiation subspace, I think. I mean, the radiation
entanglement wedge would be, so the entanglement wedge is some region of the bulk that you can reproduce by looking at observables in some subregion of the boundary. Yeah.
Yeah, I mean, one also takes into account the quantum extremal surface.
Yes. So the question of what exactly quantum means there is an interesting question, because let me get there. I think we will briefly have an opportunity to talk about it anyway. So the point being that, so it's the very loosely speaking, the calculation, the entanglement wedge calculation really does is to give a semi-classical Euclidean gravity definition of entanglement entropy. So, and that seems to be able to calculate the evolution of the entanglement entropy, but it's not clear how exactly the density matrix itself can be obtained from semi-classical gravity. Somehow semi-classical gravity seems to magically know the page curve, even though the density matrix itself is not accessible to it. One would imagine. So that it's not accessible to it because there is too much information in the density matrix, which you might not, even though the trace raw log rho is much less information in some sense. So yeah, it's just one number compared to the density matrix, which is some n times n. So that information somehow is accessible to semi-classical gravity is the way in which the entanglement wedge will resolve the information paradox in this particular the page curve information paradox. So there are much more. So the question of how to reconstruct the original data, etc., I think it is I think it is a harder question. I mean, yeah, I mean, I think that there are many things that can be said. So, but at the same time, I wouldn't say that the current developments, I don't think anybody would claim that they resolve all those issues. Yeah. Does that answer the questions?
Yes, we can talk about it later again.
Yeah. So, so the question one can ask more generally how the entanglement of the subsystem should evolve, given that the black hole, you expect that even to formulate Hawking's calculation in the bulk.
Chethan, non-physics thing, can you make your page fit page or something? It's a little bit.
That is the kind of challenge. Let's see.
see something like fit page in that thing. Go to the next fellow to the right, to the left of it. That
This guy
on that, yes, and say
full screen.
Full screen is also fine, I think.
Full screen. So Ayan was telling me that you won't be able to see my cursor if I do that, but I can try.
Yeah, we'll let you know. Just try.
Okay. Can you see my cursor now?
Yes.
Yes. It works. Yeah, it still works.
It works.
Good. So I think
everything works now. Thanks.
Okay. So, so the question is, how exactly does the entanglement entropy of the subsystem evolve if degrees of freedom are steadily leaving the subsystem into the rest of the system? This will be a model for Hawking radiation. And that's the picture. So in some sense, that's what the page curve is trying to abstract. So the result is interesting because the overall shape of this page curve is very general. And it's just, it just comes from the fact that there is a Hilbert space can be tensor factored and degrees of freedom are going from one to the other. So the shape is just completely fixed. It will be the tent shaped page curve. And so that's the good thing about it. But Hawking's result does not lead to that answer. And the reason for that is Hawking's calculation is predicated on the horizon being smooth throughout. So there is apparently no information in the outgoing radiation, and various versions of this problem has been pointed out by Page and Mathur, and variation of Mathur's argument by Ams and company. So that's the setup. So let me just flash quickly the page curve picture, which is kind of mandatory. So the straight the straight line that goes up forever is the entropy of Hawking radiation, as you might get from Hawking's calculation. But for if the system is reasonably to be reproduced by a curve like this, if you assume that some approximate bulk locality holds in some suitable sense, and this is where I think that's the question, which is somewhat of a significant question, but it seems to be the case that people are assuming that there is some sort of approximately bulk local description of a black hole as an isolated system can be done even in flat space or for a small black hole radius. So if that is the case, that's the curve that one should find. So, so the good thing about the page curve is that it brings out a more detailed manifestation of the violation of unitarity by emphasizing Hawking's implicit assumption that black holes can be localized in the bulk. And this is useful because now we have a curve to aim for when we are trying to, let's say, resolve the information paradox. And I repeatedly want to emphasize that by resolving the information paradox, I just mean this one fact: we can reproduce the page curve. And the question of, there are interpretational issues still. So it's like, yeah, there seems to be a reasonably nice calculation that you can do, which gives you the page curve is all I really mean here. So, okay, so operationally, the difference between the Hawking expectation and Page's curve happens because Hawking's version of the entropy calculation treats the entanglement entropy as entirely due to the bulk entanglement entropy of quantum fields in the black hole background, which basically means that during Hawking radiation, there are two kinds of modes: those that go in and those that go exit the system. And the entanglement entropy is relentlessly increasing because once the modes that leave the system, they are entangled still with the modes that went into the horizon. So this means that the entanglement is relentlessly increasing. And that entropy that you calculate using this bulk field theory calculation is called S bulk typically. And one can think of S bulk as the entanglement entropy of the bulk quantum field modes that have left the black hole subsystem. You can think of it that way. And if you're in the context of many of the calculations that have been done recently, this will be an AdS, AdS which is coupled to a sink, and AdS you can think of as a system, and the sink will be the second tensor factor that is necessary for formulating the page curve problem. Okay, so how can we modify this bulk prescription for entanglement entropy to get the right page curve? So that's probably the way in which it is probably most natural to think of the current developments, because Hawking's calculation had S bulk, which was this just for coming from these field theory modes, effective field theory modes. And the recent developments can be viewed as observation that there is a natural way to correct it. And that correction is, you can think of it as motivated by Bekenstein's old observation that if you wanted thermodynamics to not fail in the context of, or in the presence of a black hole, you had to add the black hole entropy or the area to the bulk entropy, bulk thermodynamical entropy. So analogous to that, one might think that adding some sort of an area term to the S bulk might be the way to get the correct prescription for the correct entanglement entropy. So this is, just an analogy, and formalization of this is what one calls the quantum extremal surface. It leads us to an idea called the quantum extremal surface, and this was proposed by Engelhardt and Wall, and that's kind of the key object that one uses in order to make these recent statements about the information paradox. Okay, so in an AdS CFT context, the idea is that the entanglement entropy of a CFT subregion should be calculated by extremizing this generalized something that, this, you can think of this as the definition of the right-hand side as the definition of the generalized entropy. And the chi is some bulk surface that is anchored to the boundary of the boundary subregion. And this, when I say S bulk chi here, I mean the bulk entanglement entropy of the field modes that live in the region bounded by the boundary subregion and chi. Okay, so this is the generalization of Sgenkai. So yeah, I don't know whether that was clear. If you have seen it, I'm just repeating things you have already heard before. But otherwise, if you have any questions, I can answer. So the idea being that there exists a bulk surface, and that bulk surface is anchored to the boundary of the boundary subregion whose entanglement entropy you're trying to calculate. And so Sgenkai is basically defined in this way. So this is a note that even though I presented that as S bulk chi getting corrected by some piece which is area, this piece is humongous because it is 1 over G. So it scales with extensively with some large n. And but that's not something that you should be too surprised by, because this is exactly what Bekenstein essentially did. He added a huge term as a correction to a small term, and that's what that was. Okay, so this is the object that so what the prescription basically is that one has to extremize this quantity, and the surface chi that extremizes this is basically called the quantum extremal surface, and the entropy corresponding to that is basically the correct entropy that one should associate to the black hole. So in AdS CFT, it is believed that it's one passing comment. So in AdS CFT, it is believed that the region within the quantum extremal surface can be reconstructed only based on the subregion data at the boundary subregion. So which means that the region bounded by this quantum extremal surface is a region that can be reconstructed from the boundary, and so you call it the entanglement wedge. So that's the definition of the quantum extremal surface, and that's in some sense the key object. So most of these things I'm just kind of giving you a general flavor. So I will kind of quickly change gears in a couple of slides and go on to what I want to say about the stuff. So, but you can ask questions if there are any more general. So okay, so it turns out so this is kind of like a one-page summary of what happened. So I think the context is in some sense more important than the actual calculations that went into these things in some way. So hopefully whatever I've said so far is clear. And if that is the case, the key point that happens. So what we have done so far is that we just changed ad hoc the prescription for the bulk entanglement entropy from some S bulk, which is a natural thing that you might associate to entangled quantum fields in the black hole background, with a new term, which is basically contains an area piece, and then there's a specific prescription for computing that. So that's what the quantum extremal surface gives you. So when that happens, so you have the point now is that, and this is where, I'll just tell you the story, is that the entanglement entropy of the boundary, so entire boundary in AdS, when the AdS is coupled to a sink, if you compute the quantum extremal surface, it turns out that there is a change in the relevant quantum extremal surface that happens after the page time. So essentially because of the trade-off between the two terms that are there in the quantum extremal surface formula. And this trade-off between these two terms, you can kind of immediately translate to a statement about the rising part and the lowering part of the page curve. So, and that's basically the calculation that Pennington did, and in a very specific AdS2 JT gravity type of setup, also by these 4 people. And that's kind of the main sort of development that has happened in the last, let's say, a year or so. So, so this is not quite so there are other threads also in this picture. So there is the first paper that I wrote with my students is actually kind of more reliant on this sort of an outlook, the Pennington, Almaeri et al. Type of approach. But so today what I'll talk about instead is actually a slightly different approach to this. And that involves two different, so it basically involves two basic differences from the setup. And the first difference is that I am not going to talk about the evaporating black hole, where the page curve has this very specific form. But instead, what I'm going to talk about is a version of the same information problem, a very similar problem, in the context of an eternal black hole, which was noted by Mathur and recently by Maldacena and collaborators. And so there's a related information problem for the eternal black hole, and there's an associated entanglement wedge phase transition that resolves that problem as well. So that's the context in which I will work. And the second point is that I will be working with what is called a doubly holographic setup. And I'll explain these things a little bit more in the next couple of slides. So, I just want to emphasize the two differences. One of them is that I'm looking at the eternal black hole version of the information paradox. And the second is that I'm not going to directly look at the quantum extremal surface, but in quantum extremal surface in the geometry, but I'm going to look at this so-called doubly holographic setup when, so I'll explain what doubly holographic is when I get to the next slide. So this is, this is a fresh set of slides. So my organization of the talk is a little bit, if I confuse you, just ask me. So, okay, so this is just a picture of what exactly the eternal black hole version of the information paradox means. And the statement is basically that if you are looking at, if you are computing the entanglement entropy, this is one version of the information paradox. It's that if you are computing the entanglement entropy of an eternal black hole, coupled to let's say a thermal bath or a system in, roughly speaking, in a constant temperature, and you can compute the entanglement entropy between two asymptotic regions which are of this type. You don't have to worry about the coordinates here, etc. So the only thing that I want to drive home here is that if you compute the entanglement entropy across two such points here, so it is going to get a contribution from this red line here. And what happens is that as the time moves forward, which means that these 2 points B and minus B are moving forward in time, both are moving forward. And it's important that both are moving forward, because if one is moving forward and one is moving backward, you can actually relate it to the t equal to 0 slice through an isometry, because it is kind of a boost in this geometry. So, so if you do that, you can see that the minimal surface, or the RT surface that connects these two things, passes through the horizon middle. And as time goes on, this region, this is something that Mathur had observed long ago, and it has been revived in these papers of Almaeri, Maldacena, and Mahajan, that this region, its length keeps increasing and increasing with time, and this increase in length is actually linear in time, and that was observed by Hartmann and Maldacena. And it's basically related to the fact that inside the horizon, these there are these nice slices whose area or length keeps increasing with time. So, and that contributes to the entanglement entropy, and because of which the entanglement entropy increases in an unbounded way. And if that's something that is nonsense, because you expect that if it is a finite system, the entanglement entropy cannot increase unbounded. So you would like it to saturate at some point, so that the entropy, maybe there is a place where the entropy goes rises up, but then it kind of saturates. That's what you would like. So, but if you look at this picture, you don't see any possibility of that, because as time goes on, these points get closer and closer to the null boundary, and these lines get bigger and bigger. Note that this is a conformal diagram, so these things are they're not really measuring the real distances, real sizes. So the surface can become arbitrarily large. And that's one version of the information paradox. So, and the point is that this, so now I will explain what the basic way in which it gets resolved is that there exists a new extremal surface that becomes relevant at some finite time. I will call it again the page time, even though it's a new, the quantity as such is slightly different as an expression from the one that shows up in the evaporating black hole. So after a certain page time, the contribution is not going to come from this this red extremal or RT surface that I've drawn here, but it's going to come from some surface that is based here, which is an island. So, and I will explain that in the context of this thing called double holography. And let me explain what double holography is. So essentially a double holography just means that we are going to look at brane world black holes. That's really what it means. And in other words, we are considering information paradox in the context of a system where there is an, let's say, at least in the context where it has usually been done, there is an AdS gravity on a brane, and then you couple it to a matter theory. And this matter theory, you take it to be strongly interacting with large central charge so that it has a dual holographic description. And then you work with, so this is the context anyway of the standard brane world setups, a certain version of the brane world setup. And then you can, instead of computing the quantum extremal surface directly, what you, the prescription given by Almairi, Mahajan, Malsena, and Zhao is that you compute just a normal Ryu-Takenagi surface. Just don't worry about all this quantum extremal surface stuff, but just compute the Ryu-Takenagi surface in the bulk, and you will see that there exists actually a phase. There will exist a phase transition in the relevant RT surface after the page time. This is the claim. So, and this prescription for doing it this way, where you specifically take the matter theory to have be strongly coupled with the large central charge, so that you have a holographic description, is basically sometimes called double holography, but it's really the same thing as a brane world system as far as I can understand. So, and this is basically the bulk in which the brane world lives. So you compute your Ryu-Takenagi surface in the bulk, and that's the basic setup.
Chethan, can I ask something?
So, yeah, sure.
So actually the Ryu-Takenagi surface in this construction reduces to QES because the gravity is switched off on the segment in which you are trying to compute whose entanglement entropy you're trying to compute, right?
That's true. Yeah. So yeah. So
and therefore,
no, I mean, it doesn't necessarily have to, because I think you're talking about some GT, so let me be precise about this. So the bulk calculation that you're doing is, so the Ryu-Takenagi surface that you're computing does not get any real contribution from the matter part in the bulk. That's the reason why it just reduces to Ryu-Takenagi.
No, that is because you're using the holography. So
right, that's right.
That's fine. But then you should, but also the endpoint itself has to be, you have to switch off gravity there, right? Which is a.
So the bulk has gravity.
No, the region in which you are computing.
Yeah.
So you basically in this setup you are coupling.
So the idea is that there is a brane world black hole. So let me maybe flash a picture. So this is the kind of setup that one talks about. So for example, so this is sometimes called a Karch-Randall brane world. So the idea is that this is the brane. So this green part you can ignore. So the brane is somehow some brane that is living here, and it has dynamical gravity on it. That's the, and then, but there is some boundary condition here, a transparent boundary condition. So this is AdS gravity on the brane, and then there's a transparent boundary condition. And this boundary here is the gravity is frozen. So
yeah, exactly. Yeah, that's very crucial. I think, no, that's very crucial to this setup.
It's crucial in what sense? I didn't.
Yeah, it's. Yeah. Otherwise,
you can. So for instance, you can compute extremal surfaces. So you can compute a Ryu-Takenagi surface here, for example. That's what people do. So this is the kind of calculation that, for instance, in that AMMC paper is there. So so if you want to model AdS gravity coupled to a external system like a sink, then this is a good setup. Okay. So
yeah. Otherwise,
this is the context, and that's the context in which people have done some of these calculations. Yeah. So I guess that's what you're
so if you have if you have also gravity induced on the boundary, if there's induced gravity on the boundary, then it also gets contribution from the endpoint. So in the context of JT gravity, you have the value of dilaton, for instance. Mm-hmm. It is important that you kind of switch off you make the dilaton infinite on this.
Right. So
on this part
yeah. So for instance, yeah, that's true. So if you want to compute an entanglement entropy here, and if there was, in principle, the area here will need a regulator because it is going to infinity. It's going to bound. Is that what you're trying to say? Hello?
Yeah, no.
Yeah.
Okay, anyway, I mean, I think it is going to come to your talk. So,
yeah.
I was somehow of this opinion that what one wants to do in this setup is that you couple a gravitational system to something that is not not gravitating.
Right.
The computation well defined.
This is the so there has to be at least an approximate notion of tensor factorization. So, for instance, I don't think people believe that even in flat space, it is you just need to have a way of isolating the black hole. There are people like, for instance, I think one of the things. So, if you look at one of the recent reviews of Maldacena, he basically talks about he's just all completely in flat space. So where there is a region. So as long as you can take the black hole to be some isolated region, contained in some isolated region where the black hole, and then the rest is a sink, I don't think there is any real problem. I mean, so I think the one issue is that nobody knows what the controlled approximation where one can do that is, and that's one of the issues that I think ultimately will have to be resolved. But the general I think that so because ultimately, the ultimate question in some sense is that what is so if the two observables in AdS CFT we all agree is basically things which are basically CFT offerings, right? So we don't expect them to be living on the bulk. So there is, if you have
Chethan?
Looks like we lost Chethan.
Yeah. Okay, hopefully, I think he will come back.
Yeah, just wait.
Hi, Chethan, you're back. Chethan, can you hear?
Can you hear me?
Yes, Chethan. Yeah. Now we can hear
so
you.
what I was saying was that the power went off here, unfortunately.
Oh, no problem.
So,
okay.
Fantastic.
But we can resume your talk.
We want to see your slides.
Yeah.
You can see my slides, right? So I've turned off my Wi-Fi on my phone. So that's how I'm back online now.
Okay.
So you might not be able to see my face, which might be an advantage, but otherwise I think we're okay.
No, we can actually see you, but now you have to share your screen again.
Actually, your face is now much clearer now.
Yeah.
You have a very,
it's
looking like a Roman painting.
Yeah. Share your screen again, I think.
Okay. Is it okay?
Yes.
Perfect.
Can you
Perfect.
Okay, good. All right, 1 second. Okay, yeah. So viewers, I think you were asking something.
No, we can just move on. We can move on. Something.
Yeah, I think that's probably better. So
the question in the previous diagram, can you explain what is the boundary subregion for which the red line is the RT surface?
The previous the boundaries. So essentially, so the point is this is so it's minus infinity minus b and b comma infinity. These two
segments.
And so like, okay, I think so the way to say that is basically this is not a here it is essentially a calculation. This is a calculation that is done directly. This is not a holographic calculation. So what is being done here is that this is a JT gravity, which is a two-dimensional theory, and in that two-dimensional theory, so you have a bulk AdS2 gravity, AdS2 or this JT gravity, and then what you do is you compute entanglement entropies using this Cardy-Calabrese type of formulas. So it gets contributions effective. So the point being that the entropy gets contribution from a segment of this type. That's the point. That's the more accurate way of saying it. It's not really a holographic calculation in this particular case because it's two-dimensional. So one of the reasons why people have done that in 2 dimensions is because gravity coupled to CFT, you can compute entanglement entropies of the S bulk that I wrote down earlier directly in CFT because you know these Cardy-Calabrese type stuff. So that's one reason why people do that in AdS2. So yeah, maybe, yeah. So, okay, so where, yeah. So the only picture that I wanted to, so the picture that I wanted to show here is, I think that we are already here. So this is sometimes called a, so I think I also have to make the slide again a little bit bigger. Sorry, no, I think it made it worse. Is that okay? Hello, is the slide, can you see the slides?
It seems so. Yeah, yes.
It's fine, fine.
Okay. Okay, so this is this kind of a brain world is sometimes called a Karts-Randall brain world, and so this is specifically tied to the fact that you are coupling AdS gravity to a sink, and the sink is supposed to be a region where there is gravity is not there, because this is the original the AdS CFT is the context where you expect that you have some control on various things and such. So but at the same time, so what is the so the original formulation in which Pennington and company formulated it was where you had AdS, and then there is a coupling to the sink, and this subcritical Karts-Randall brain world is kind of tailor-made for that kind of thing. So, but the question of, but I think it is the people who expect the these islands to somehow reproduce the Page curve. I think the expectation that it works more broadly than AdS, I think is I think that is the broader perspective, I think. Okay, so I will talk about some counter arguments to that along the way, because that's kind of relevant to what I'm saying. Okay, so the geometry, so if you want to do this doubly holographic computation of this extremal surfaces, so what you do is you compute these RT surfaces. So here I'm looking at a specific brain configuration, which is where the angle is pi/2. So this is taken from a paper by Karts and Geng, but the angle of this brain can in fact be less than theta, and even then there will be some extremal surface like that will go here, but then you'll have to really solve some nonlinear Einstein equation to solve it. So the point being that there exists two kinds of extremal surfaces if you are looking at the boundary theory. So this is the brain where gravity is supposed to live, and this is the place where the sink is. And what you're trying to compute in some sense is the entanglement entropy of a region which is far away from this black hole that is sitting here. And there are, when you compute the entanglement entropy using this RT prescription, this brain world RT prescription, then there are two RT surfaces that are relevant, and one of them, so note that this here is actually it's a planar black hole in AdS. So this is a planar black hole, and this is the brain world where the gravity and the black hole that you are interested in lives. And the claim is that there exists two of these guys, and the trade-off, so the phase transition is basically between these two guys. And the thing that I said before is that this extremal surface, the one that cuts the brain world, sorry, the planar black hole horizon, as time goes on, its area increases linearly. So that's because of the fact that the wormhole connecting, this eternal black hole type of thing, the size of the wormhole is becoming bigger and bigger with time. So at the beginning, if this point is sufficiently far out here, you can imagine that this length is actually smaller than this guy. So the phase transition is actually, so initially this is the RT surface that contributes to your entanglement entropy. But as time goes on, because of this linear increase in its length coming from the inside horizon part here, you get a phase transition onto this, and that you can see is a constant. It doesn't increase with time, and that's how the entropy saturates. That's the picture. So is that picture clear?
Yeah, Chethan, I just want to just clarify one small thing. Yeah. So this region R that you are, so that is the entanglement entropy of this region R that you are trying to compute, right?
That's right. And that's where I think, in order to make a statement, for instance, when there is dynamical gravity here, you have to assume that this region, the black hole region, is sufficiently isolated, and there is this region is somehow, it's some sort of an asymptotic region, let's say in flat space, something like that.
Yeah. And then obviously, if you switch off gravity in R region, then obviously your QS will reduce to just your root Takayanagi surface, right? Because it's simply it will simply be the root Takayanagi surface. You don't need this extra correction. I think that was the point of the construction. So, Chethan? Looks like we have lost Chethan again.
Maybe power has come back now.
Okay. Yeah, the Wi-Fi switches on and switches off every time this happens, no?
Yeah.
Hey, Chethan.
Yeah, I'm back.
Did the power come back now?
It came back, but there was some other issue. I think. Yeah, the power came back. Power came back. So.
I see.
But so let me just So can you see me?
Yeah. We are back.
Slides?
We are back. Back
Okay.
to your slide. Yeah.
The power going off. Yeah. Okay. So yeah. So there is a divergence coming from this end of the RT surface, but because you are comparing against two objects and they both have the same divergence, it doesn't really matter. That's the argument. Okay. So I think this slide I've already explained. Yeah, so this is coming to, so this is, in some sense, this is the point that I kind of want to get into in some way, which is that, see these, when you have a brain world system like this, what happens is that the gravitons, so the gravitons here are massive. The gravitons on a brain world, AdS brain world, which is with a transparent boundary condition, it has been shown that the gravitons there are massive. And so the mass of the graviton is related to this angle theta. So if the angle is small here, the mass of the graviton is smaller. And when the angle becomes, theta equal to pi by 2 is really like a very, it's a very heavy graviton. So it's not very interesting, but conceptually it's the same. That's why they have drawn this picture. So when theta becomes smaller and smaller, the mass of the graviton becomes lighter and lighter. But along with that, what you have is that the G Newton also goes to 0. And the brain also goes to the boundary, and there is no gravitational dynamics, and there is no information paradox, and there is nothing really happening. Okay, so the question is, I think that, so one of the question that I kind of want to look at here is the question of whether the massiveness of the graviton is a result of the transparent boundary conditions, the AdS boundary. Is it a consequence of that, or is it more fundamental? Or more precisely, whether the fact that the island physics is relevant, can you attribute that directly to the mass of the graviton? That's the question. So, so this is the basic question that we would like to address. And so the latter would be problematic for islands as a general solution to the information paradox. If massiveness of gravitons is essential for islands to exist, I think it is fair to say that then it cannot really be a solution to our flat space gravity or anything like that. So what we would like to see is if there is a version of the information paradox that can be phrased in the critical brain worlds of the usual Randall-Sundaram 2 type. So what that means is that, let me draw a picture. So I'll just go down real quick to a slide where maybe I have one slide somewhere. Yeah, so this one. So you can forget about this green stuff. What I really mean by that is that the brain world is kind of flat like this. And there is no, the brain is not going to the boundary of AdS. That's what I mean by that statement. So, so in such a brain world, you don't have a cosmological constant, but at the same time, you have G Newton. So the problem in some sense in this Karst-Randall brain worlds is that there is only one parameter, this theta, that controls many different things. It controls the G Newton, it controls the mass of the graviton, and it also controls the cosmological constant on the brain. So, and all of them go to 0 in the limit when the theta goes to 0. And so you can't really tell whether it is the mass of the graviton that is creating the problem, or maybe more obviously, the fact that the G Newton is going to 0. If the G Newton is going to 0, you obviously do not expect any information paradox. So what we would like to have is a setup where G Newton is finite. And, so, and one such example is this Randall-Sundaram 2 type of brain world, where it is basically just a cutoff in AdS. And you have no cosmological constant on the brain, but the graviton is massless and G Newton is finite. Okay, so this is the kind of setup that we would like to look at. So, so the question is whether we can have a doubly holographic picture for black holes in such non-AdS brain flows. Is there any evidence at all for islands in this kind of geometries? Islands means, is there any extreme of the kind of extremal surface picture that I drew here, where there are two kinds of extremal surfaces that naturally exist? Is there any possibility that we can find such two extremal surfaces in that context is the question. I don't think I will be able to completely convince a skeptic, because to fully answer this question, you have to go to higher dimensions, and the kind of things that I'm doing, you'll have to do fully in higher dimensions. But I think that, and in higher dimensions, the calculations must necessarily be numerical. But I expect that because of some things that I will tell you, I think that the structure is fairly robust, and I think that it should exist in higher dimensions. So this is the claim. So is there any question about the premise? So is everybody there? Can you hear me? Yeah.
Yeah.
Okay, good. Okay, so this is the setup, and so the proposal is basically this: that we will argue that a natural place to look for such islands, or a place where island physics can emerge, is when there is when in the context of the so-called AdS black funnels, AdS black funnel geometries, when they're attached to a brane world. So, and it will seem like somewhat of an esoteric construction. So I'll slowly build up to that. You know, what exactly is an AdS black funnel, and why is it that it is not, you know, just something that I pulled out of a hat. So, and AdS black funnels attached to brane worlds. Why are they relevant for the brane world information paradox? That's flat, you know, brane world information paradox where there is no cosmological constant. That's the question that I would like to kind of make some comments about. Okay, so just as an aside, I also want to say that there is, you know, so this is the doubly holographic picture. So we can also make some statements in a context where there is a non-brane world, or, you know, so a calculation or structures more analogous to what Pennington and company have seen. You can also talk about those in the context of flat space. That's what I did with the students. But there are many papers on flat space information paradox. Many of them agree with us in various ways, but generally in lower dimensions. And the higher dimensional paper, I think I should just point out that there is a paper by Alok and Subrat and company where they disagree with us. I mean, but their paper came out before us, so kind of they, you know, proactively disagree with us. So, but yeah, so I mean, I won't have anything to say about that today, but I just wanted to point out that for the purposes of full disclosure. Okay, so so yeah, so let me come back to my black funnels. So the claim is that AdS geometries were black holes. So what are black funnels? So AdS geometry. So I'll just start by talking about what black funnels are in the context of AdS CFT, and then I will talk about what AdS black funnels in the brane world are. Okay, so AdS geometries were black holes. So black funnels are basically systems where you have a boundary black hole. So, you know, on the boundary you have a black hole space-time, but then it's not dynamical because the boundary of AdS CFT is non-dynamical. So it's a black hole in the boundary, and the idea is that you construct bulk geometries which are continuously which are in some sense continuous extrapolations of the boundary horizon, and that is this picture that I drew somewhere down here. Too far away now. So this is the kind of picture that you can take a look at. So this is the boundary. You can ignore all this extra junk that is here. We'll come back to that later. So this is the boundary, and then there is a funnel structure that is sitting here, and these solutions in the AdS CFT context have been constructed. So it was first constructed analytically. So note that there are two kinds of objects. One is the AdS CFT black funnel, which is anchored to the boundary, and then there is a question of a brane world black funnel, which is ultimately the thing that we are interested in. So right now I'm just talking about the AdS CFT black funnel, which is anchored to the boundary, and there is a boundary horizon. So the boundary is basically just some black hole living in some flat space or some appropriate slicing of AdS. So that's the picture of an AdS black funnel. And so the idea, so these things were constructed almost 10 years ago now by, first they were constructed in the context of some analytic solutions using these things called Plabansky-Demiansky classes of metrics, which are analytic solutions. But those analytic solutions are asymptotically hyperbolic and not asymptotically flat. So you can foliate bulk AdS spacetime not just with flat space or spheres, you can also foliate with the hyperbolic spaces. And in such, so these AdS metrics, which are the ones that Plabansky and Demiansky constructed, they can be used to construct these black funnels in asymptotically hyperbolic background. So there will be a black hole living in an asymptotically black hole living in a hyperbolic geometry, and they have bulk continuations which are black funnels, which are the solutions that Hubeny et al. Constructed. And the good thing about them that they're analytic. The bad thing about them, they are not asymptotically flat on the boundary. Okay, so I don't know whether the picture is clear. So So sometimes I'll talk about asymptotically flat on the boundary, which means that there is a black hole on the boundary. And again, I want to emphasize it's a hardwired black hole. The metric is not black reacting, and asymptotically it's flat. And so there exists bulk dynamical gravity solutions which are funnel-like and which end on these boundary black holes. And these are the ones that Hibany et al. Constructed using this AdS CFT metrics. So the point is that the idea is that these black funnel solutions are believed to be duals of strongly coupled Hartle-Hawking states on the boundary. So Hartle-Hawking states, even though people always talk about Hartle-Hawking states in the context of flat space black holes, one important fact about them is that they really only exist if the gravity is not dynamical. Because if the gravity is dynamical, what happens is that the Hartle-Hawking state is basically a black hole in equilibrium with thermal radiation. And if there is thermal radiation in the bulk in a gravitating system, you expect that the space-time is actually a cosmology, because you will have, it's a radiation, so radiation dominated FRW like cosmology. That's the space-time that you will expect. You don't expect it to be empty, Hartle-Hawking state. So the Hartle-Hawking state is really a black hole in a fixed background, which is in equilibrium with finite temperature radiation. And that you can do with the boundary of AdS. And that's the reason why people expect that these black funnels are dual to those states in the strongly coupled deconfined matter on the boundary in equilibrium with a black hole. And the dual of that would be basically a black funnel. So this is the picture.
So,
okay,
sorry,
so,
Chethan, can I ask something?
Yeah,
so,
absolutely.
So are you trying to formulate the information loss paradox in the boundary without dynamical gravity here?
No, I'm not going to talk about, so the boundary, I'm going to use the boundary as a crutch for going to a brain world version of this black funnel. That's
I see. Okay.
So those things have actually not been constructed. So, so there is, but I have talked to people who know these things, like, some GR people, so some numerical relativity people like, Santos and people like that. And they seem to think that they will exist. So I will give you some arguments for why I believe they will exist, but you should take the opinions of Santos and other people more seriously. So, but they also do think that it will exist. It exists. So I just want to motivate the context, because black funnels, I don't think that they're probably widely known among string theorists. So I just want to give some context. That's all. Yeah. So I'm definitely not going to formulate the information paradox in the context of this this boundary Hartle-Hawking state, because that's just a fixed background. Okay, so so these analytic funnel solutions are known, and this is what I just mentioned. So, but you might think, but the good news is that there exists these AdS CFT black funnels, which means the boundary is the Hartle-Hawking state. They exist, so they have also been numerically constructed in AdS5. The problem is that they are numerical, so you can't really do anything with them unless you actually construct them yourself. So, but they do exist. There have been papers by Santos and Wei where they actually construct these boundary black holes, boundary Schwarzschild black holes, which correspond to which are the boundary of these AdS5 black funnels. And in AdS5 and AdS4, people have explicitly constructed numerical black funnel solutions. So that I will take as, so the existence of AdS CFT black funnels, I'll take it as a fact. That's the basic point. Even with the asymptotically, even when the boundary is flat. Flat means with a black hole with asymptotically flat boundary. Yeah. So the point is that, however, that's not quite what we want. What we want is basically a geometry where there exists actually a black hole in the brane world. And the question is whether they exist or not. So the key point here is that whenever there are black holes on the boundary, so for a specific class of black holes on the boundary, these two gentlemen have constructed a specific black hole on a brane world, starting from the original AdS CFT solution. So this is not a black hole that is it is not the dual of a Hartle-Hawking state. It is basically the dual of a black hole that is living in the boundary, but asymptotically it's empty. So which basically means it's more like an Unruh or Boulware or some such state. It's not the Hartle-Hawking state that one would like, where the boundary, the black hole is actually living in equilibrium with some boundary, this thing. And the way you fix that is if the boundary is at a finite temperature, if the boundary corresponds to a finite temperature thing, you expect that the black funnel, so let me just again flash the black funnel picture once again. So this black funnel, the picture you see here, so the point is that this region here, the planar black hole horizon in the bulk, is what dictates the fact that, so there is finite temperature here, and that's the reason why you expect that the boundary black hole that is living here is in equilibrium with thermal radiation here. So that's the picture. So what they constructed, so these Figueres and Weissman, what they constructed corresponds to a more like a black droplet, where the asymptotic region, this region is basically just the Poincare horizon of AdS, and there is a black hole, bulk black hole, which is intersecting the boundary. So that's the kind of structure that they construct. But the point I want to make is that there exists systematic ways of constructing brain world black holes, starting from these boundary black holes of AdS-CFT. And so because of this, I will assume that one can construct even for this, even for these black funnel spacetimes, you can construct brain world black holes, which correspond to black brain, sort of a black hole here in equilibrium with radiation here. And an important point about this is that, and this was emphasized to me by Karch, is that when you have that, and this is again related to the fact that it's a cosmology, is that these brains cannot be static. So the idea is that if you, so let's say this is the brain world horizon, this region here, the place where the brain cuts the horizon, and this is the brain, and asymptotically, this is basically like this is a brain that living on top of a planar horizon, and you can, there are general arguments you can make to see that this brain has to move upward. So if there is an accelerating brain, and then you have a Robertson-Walker cosmology living here. So this is basically a black hole living on a FRW cosmology. Note that this is consistent with what we were saying before, which is that true Hartle-Hawking states can only exist if your gravity is not back reacting. So the matter is not back reacting on the gravity. So that's the picture that we have. And so the key point is that, so we expect that such a construction can be made. Any questions? Okay. So yeah, so the idea is that, so now what we will do is that we want to kind of motivate that there can exist extremal surfaces. We want to identify certain extremal surfaces living on it. So I've already exceeded my time. So what I'll do is I'll kind of skip some of these, the reasons why I expect a certain kind of extremal surface. But the key point I want to make is that if you take some far away region from this black hole, this is kind of like the asymptotic region of a...
Take 15 minutes more, I think, right?
Yeah, sure, Chethan.
Because you lost a couple of times, you got broken off, and we started
broken off also. Yeah.
So I mean, I don't think so even if so I think I'll basically tell you the general story here, and then go on to a short calculation in 3 dimensions, and then explain if there's still time left, some cosmology facts. Let's see. So the point is that there exists, so you can construct these extremal surfaces. So the point is whether there exists extremal surfaces of this type. This is what I want to kind of find evidence for. And this is hard. So this is hard to, so the basic striking point about these extremal surfaces is that even though so there are 2 kinds of extremal surfaces. One that start from here and they just fall into the funnel horizon, so the planar black hole horizon. These are the ones that at late times will increase in area linearly, and which result in the information paradox. And then the non-trivial ones which lead to the island are the ones that I have drawn here, which basically lead to the key point about them is that they are bulk horizon straddling extremal surfaces that are anchored to the boundary. So the question is whether there exist such extremal surfaces in the black funnel spacetime. And the question is hard to answer because these solutions are only known numerically, and except in AdS3. So that's where we will do the calculation. Okay. So let me skip all these things. Yeah. So the key thing that we want to find evidence for is whether there exists bulk horizon straddling extremal surfaces that are anchored to the asymptotic region of the brain. So that's the question that we want to answer. Yeah, so here are some caveats, basically. Yeah, so let me just go through the slide just quickly. So, so our motivation for believing their existence is threefold. One is that, in the case of this AdS black funnels, AdS systems that people looked at, like the AdS with sync systems that people looked at, the basic reason why I wanted to look at black funnels is that black funnels have a structure which is actually very similar in many ways, like the horizon structure of those pictures that people have drawn. So that was my motivation for looking at black funnels. And the second thing is that in 3 dimensions, we will see that we can in fact construct extremal surfaces which are very similar to the ones that we want in higher dimensions as well. So that we can explicitly see, because in AdS3 there exists an explicit analytic black funnel. So of course you might complain that in AdS3 there are no propagating gravitons, and forget gravitons being massive versus massless. There is no gravitons in a, there are no interesting gravitons at all. So but so I can't really defend it. But what I will say is that I think the geometry is what is really responsible for the extremal surface, and the propagating or non-propagating nature of the gravitons probably not very significant is what I think. So, but yeah, I mean, I think the question is somewhat open still. So anyway, so this is the statement. And the third statement is that, as I was saying, these geometries are cosmological because the brain is forced to move. Because there is a planar black hole horizon, let me flash that picture once again. So because of this planar black hole horizon, if you just keep a brain here static, it will just fall into the horizon. So you have to make sure that it is accelerating upwards, and that acceleration has a very natural interpretation from the brain world point of view, which is that it is a cosmology. It's an FRW cosmology. So it's a black hole sitting in an FRW cosmology is the geometry that you'll have. Okay, so now let's turn to the AdS3 calculation. So the AdS3 geometry basically has this kind of a structure. So it's like there is a bulk horizon, and this is also a horizon. That's an important point. Or it's like, so this is why it's called a black funnel. It's kind of degenerate in the sense that it's like, it's just a, it's just a line. But because many things become sort of trivial and degenerate in 3 dimensions. But the general picture that so what we are going to look for is the existence of an extremal surface that goes like this. This is what we are going to try to identify. Of course, there exists an extremal surface that falls straight down into the planar black hole from far away, but we'll also try to find one that goes like this. This is the setup. So, so yeah, I mean, Z equal to 0 is a boundary. So Z approximate equal to 2 is the planar black hole. So you go farther out and farther out in the X direction. As X goes to infinity, you get the funnel becomes more and more like a planar black hole. So this is the place where the action is happening, and that's the place where the funnel is in this setup. Okay, so again, I can skip all these things. These are kind of mostly details, and the conclusion is all that matters. So yeah, so this is the geometry of the black funnel. I mean, it's just, again, it really doesn't matter too much. It's just that geometry gives you a specific structure. So because there are explicit formulas, the key point is that you can formulate the extremization problem to find the RT surface completely explicitly. That's the only thing that you have to take away from this slide. It really doesn't matter what these functions are. So, so I think I already explained the structure of the geometry. So let's just flash this again. So this is, so this is the planar black hole, and this is the place where the funnel is, and X going to infinity corresponds to the asymptotic region on the boundary directions. Okay. So the point is, so we would like to construct explicit. So we want. So let me. So let me flash. So let me just show this integral here, which is the expression for the extremal surface. So you can find what the so this is the expression that you have to minimize in order to find extremal surfaces. And what I will try to construct is basically, I'll try to construct a horizon straddling extremal surface, which goes from the middle. So, okay, again, I have to go back. So I want to construct a horizon straddling extremal surface that starts from here and goes like this. So I'll put some boundary condition here, and I'll put some, I'll fix the Z at some X equal to X naught to be 0. And then I want to find an extremal surface which corresponds to something that happens here. So this is what I want to do. So, and so this is the expression. So G is some complicated function, and it's not really, very illuminated. So the point is that this is messy. It doesn't simplify as a variational problem because it mixes everything. And if you write down the variational equation, it's the only advantage that it has. It's an ODE. So because it's an ODE, we can explicitly solve it on Mathematica. Yeah, I mean, I won't write down the equation because it is just messy and not very interesting. So, but the point is that you can solve for it with these boundary conditions. These boundary conditions that I have put, X equal to 0, so basically the kind of extremal surface that I'm looking at, and you can see that I can integrate these, the kind of extremal surfaces that I find are precisely of the form that I would like, which is that I can start from near the the funnel and I can go all the way out. Note that this is picture is kind of invert, so the upside down version of the picture that I drew of the black funnel in 3 dimensions that I drew before. So this is your horizon. So this horizon, this is basically the planar black hole horizon. It keeps going forever. But there are these horizon straddling extremal surfaces that start very close to the tip of the horizon and go all the way out to x equal to 0. And another interesting feature, another important feature, which is a property that people have seen in lower dimensions as well, is that as you go to further out and further out on this x naught, you go closer and closer to the horizon. And this is an important fact also in some sense, because it basically means that you're kind of trying to hope that your expectation is that if you have more of the asymptotic region in your so the system is in the 2 tensor factors that you might think of in your black hole coupled to the external system. So if you have more of the second tensor factor, then you would be able to reconstruct more of the bulk. So if you're going farther and farther out, on the other hand, you have less and less. So you're basically reproducing things closer and closer to the horizon. So it's a known fact in lower dimensions that the place where, so the island gets closer and closer to the horizon as you take your system farther and farther out. So this is a known fact. So it is good that, hello?
Yeah, we are there.
Oh,
we can hear you.
There was some power supply thing again happened, so I was a little bit worried. Okay, so the picture is consistent with what we have seen before. So that's in some sense, I think that particular fact I'm emphasizing because that again is very island-like. So those 2 facts in AdS3 are kind of strongly indicative of islands. And so of course we also have to have this trivial other kind of extremal surface, and there it is slightly better to write your integral that I wanted. There's the same integral but slightly different way of, I treat the independent variable in a slightly different way, and then you can actually easily show that any vertical line in the at least near the asymptotic region, any vertical line in that that cuts this thing. So any line like this is actually an extremal surface. So that's precisely the first kind of extremal surface. So we have both kind of extremal surfaces, is the point that I wanted to make, even in this funnel geometry where there is no AdS on the brain. AdS, like this is, of course, this is an AdS CFT calculation that I'm doing. So, but AdS CFT in the sense is an extremal surface that I'm identifying in AdS CFT. So that means that, there is, but the question is, but this is very suggestive of the fact that these extremal surfaces might have natural interpretations on the brain as well. So this is the reason why it's worth doing them. Okay. So I think that's all I will want to say about the extremal surface. Any questions? I was kind of fast through there, but I think I just emphasized the main points. Any questions that I can try to answer? Maybe I'm going a little too fast.
Any estimate of the page time or something?
Sorry?
So you have your two extremal surfaces,
right?
And you should compare them, right?
Right. So that's related to, so it's proportional to the temperature of the planar black hole and the entropy of the planar black hole. That's roughly the, so the page, so the only thing, in all these calculations, what people do is that they just show that there exist these 2 extremal surfaces. Even in the AdS cases, what they do is that, because many of these calculations, like really determining these things is tough. So, but okay, I'll say a couple of comments I'll say. So the first statement is that what people do is that they show that there exists both these kinds of extremal surfaces, and then it automatically follows that the first trivial kind is always going to be time dependent because it cuts the planar black hole horizon, and the second one is a fixed quantity. So that's the key point. So, and it starts out with the first guy, and so after a while, the phase transition happens to the second guy. So people do not really estimate the times at which this is happening. And that's an interesting question, because even in AdS cases, even in the AdS brain world cases, I often feel that, there is a dependence on that theta that I showed you, which actually can be made arbitrarily large so that it can be parametrically larger than the page time is a suspicion that I have, which I have not seen really addressed in many of these discussions. But in our case, well, I mean, we don't have really much of a problem of any of these things because all of these things are manifestly finite.
But if that is true, this has no connection with the page curve then.
Well, I mean, so so it might be the case, yeah. So, but the fact that there exists a phase transition, I think it is still non-trivial. So, I completely agree with you that, even in the ADS, so there are two things. One is that this problem, if it exists in ADS brain worlds as well. So, and I think it is worth a systematic study of how much of parametric dependence on these things it has. So that's, I think, definitely worth looking at. And the second point is basically that, so the second point is that the fact that there exists a phase transition, there exist these two kinds of very natural, extremal RT surfaces, and one of them which has late time dependence, and the precise structure that is required for the phase transition to happen, I think that is non-trivial. So you didn't have to have this to happen on a brain world, or on a funnel to have this kind of an extremal surface. So the fact that they exist, and the reason why we tried to calculate this, of course, because we wanted to see whether there was something of the kind, and then you find this, then I think there is some, well, maybe there has to be a better explanation for it, but I certainly think that it's not, there is a phase transition, that much, let me leave it at that. So I think the rest, I think, we'll deal with later. Okay, so
thank you.
So that partly addresses what Suresh's question is, I think. Or have I not addressed it at all?
Yeah, no, you did. You did.
Okay, good. So coming back to this, so the thing is that what we showed is basically, so this is just basically the same thing that I just said, but except the key point now is that the brain is moving, and because of which the cosmology, on the brain, what you have is a cosmology. Okay, so we'll have to find a way to keep track only of the black hole contribution to the entanglement entropy, because if you compute, because the brain is moving, these extremal surfaces are constantly there. If you just look at the size of these extremal surfaces, they are just increasing, because the brain is moving, and that so the location where the brain is attached to is put on the bulk is directly related to, in some sense, the size of the place where the anchoring surfaces are for these extremal surfaces, for these RT surfaces. And so the size of the contribution to the entanglement entropy coming from these things is constantly rising, at least naively. So that seems like a problem. So you have this extremal surfaces and their sizes are constantly increasing. So what are you supposed to do? So which means that both these extremal surfaces are actually time dependent. Might superficially seem like that. Okay, and so I will argue, so we'll have to find a way to keep track only of the black hole contribution to the entanglement entropy. And a related fact that I want to point out is that even if there was no funnel, if it was just a planar black hole and there was a brain sitting on this geometry, it also accelerates, and it basically gets this time dependence in its areas, or the RT, this entanglement entropies, because of the fact that the brain is moving there as well. So it's basically happening because of a cosmological expansion. So the radial position of the brain translates to the FRW scale factor on the brain world, and so what we are seeing is basically a cosmological production of entanglement entropy, which we are somehow, it's not really the thing that we want to keep track of if we want to understand the statement about black holes. So the question is whether we can actually do it in a systematic way. So that's not obvious. If you can't do that, then finding these extremal surfaces is fundamentally not very interesting, because the only entanglement entropy that the system is aware of is the one which includes both the cosmological contribution as well as the black hole contribution, and we don't know what to do with that. Okay, so okay, so so because the slides are a little new, I'm trying to remember what I said in the slide myself. So okay, so so this is the stuff that I said, which is that because the brain is moving, you have a natural FRW scale factor, and the point is that the place where the funnel is attached to the island is attached to the brain, there is a time dependence, and that time dependence will actually make the entire contribution have a time dependence, and then this is going to be we don't know whether it is how do we extract the black hole part of the entanglement entropy is the question. Okay, so but the point is that so the horizon that we had in this brain world picture that I drew of the funnel, that the horizon is also getting stretched because of the fact that the brain is moving up. And so this is something again that I have asked some numerical relativity people whether that they think that is plausible, or the fact that it stays fixed, and they have told me that it is the brain. They also suspect that the brain is going to move up, even though nobody has really done this calculation. This is another point where it's like it is important to kind of have some clarity, because but one thing I'll say is that if the brain is not moving at all, then if the black hole part of the brain is not moving at all in this AdS black funnel brain worlds, then the calculation of the subtraction business of two separate RT surfaces already would work out. So the more interesting scenario is if the brain is moving up. So let me again flash that slide. That's an important slide, but I can only put it on one. I mean, I could have probably put it in multiple places in the talk. So this is the picture that I'm talking about. So what I'm saying is that this brain is rising. So there are two natural ways in which can happen, that the brain world horizon is also rising along with the brain, or maybe it gets somehow stuck here, and it is only this region which is close to the planar horizon, which is parallel to the planar horizon, that is rising. And if that is the case, there will be no Robertson-Walker scale factor that is experienced by the black hole horizon, and there will only be a FRW scale factor in this part. So, but if that is the case, the comparison between these two things will be completely trivial, and there will be no, it will be the same thing as what people have done before, because the island does not come with any extra time dependence, and everybody, so the information paradox is already solved. But the reason why it is not that trivial and it's more interesting is because it's natural to expect that when the brain is rising up, the horizon, the brain is just moving up, and the horizon is also moving up. In other words, the horizon is actually feeling the Robertson-Walker scale factor. And so that's note that is kind of consistent with the fact that if you take this all the way to the boundary, so you do have a planar, you have a black hole in the boundary. So if the horizon was to get stuck here, it's not so intuitive that if you go all the way up, why should you have a horizon here? So that's not very intuitive anyway. So, but these are very schematic arguments. But nonetheless, the point I want to make is that it's plausible that the horizon of the black hole, of the planar black hole, the horizon of the brain world black hole is also getting stretched because of the brain world cosmology. And we want to understand how to do our calculation of RT surfaces in that context. And
it seems to me the second possibility is more reasonable, because usually what has been seen in all these computations that the location of the QES actually captures the Hayden-Pascal time. And if your one end is really in a cosmological context, it would naturally, there will be some redshift factor, right?
Yeah. So the point is that, so what I will say is that the redshift factor, there is a very natural way to take care of the redshift factor. That's in some sense the point. So if you have a redshift factor, anyway, the argument doesn't work. So if there was actual time dependence at what you're saying is that it should not be time dependent, or otherwise the calculation is, it should not be there should not be any time dependence coming from the island part, or
no. I was saying the opposite actually, because
there should be a time dependence.
Yeah, I was saying the opposite, because if you have to capture the Hayden-Pascal time, then it's more natural to put
so I don't know exactly. So there is a time dependence. That's my point in some sense, which is that your bulk. So the brain, because the brain is moving up, the brain world horizon is also moving up, which means that the horizon is expanding according to the scale factor, which makes it time dependent. That's precisely, if that's what you're saying, we agree. I'm just saying that, I was just giving you some motivation to think that it actually does that, because there is no explicit solution. In some sense, I would say that is the one point which is hardest to kind of form an intuition for without having an explicit numerical calculation. So all the other things that I'm saying, I'm fairly confident about. So but I can't really be 100% sure that the horizon that's cutting the funnel is actually expanding with respect to the scale factor or not. So that's the point where, so I would say that, so the two arguments that I have, one is, Ian seems to think that anyway it has to expand, in which case I'm happy. But I'm saying that, like, so I have talked to some of the numerical relativity people, and they seem to think that it will expand. So that's their intuition. And the third reason that I think is kind of reasonable is that if it is moving up, you kind of do, like if we do have a brain of AdS funnel attached to the boundary. So there exists a black hole living on the boundary of AdS. And if there was no way in which this brain world black hole had no, I mean, I would think that it is more natural for this brain world black hole to have a continuous limit to that boundary, where this scale factor is basically the conformal, the radial conformal factor. So I would imagine that it is just that. This is the natural continuum limit of the natural boundary limit of the brain world. So those are a few arguments for thinking that it moves. So, but if it moves, then we have the burden of explaining why is it that the time dependence there doesn't affect our argument, or find a way to extract the black hole thing. And here is where I think, so I think I said all of those things. Okay, so these are kind of somewhat, well, I mean, I can come back to these slides if people are interested. I'm just trying to give some reasons why the information paradox problem is reasonably well defined, or well defined in the context of these, even when there is an expansion. That's what I was trying to say here. But I think the more interesting point, I can come back to that if there is question, because it does require some explanation. But so I think the more interesting thing here is that what one should really calculate when you're computing entanglement entropies on the brain world are, so the proposal is that basically what you should compute is the co-moving entanglement entropy. And so the reason for that, there are a bunch of different reasons why this is the natural thing. And one reason is that if you're computing the co-moving entanglement entropy, what it really means is that you have a fixed cutoff in the co-moving scale. And what that means is that modes that get redshifted because of cosmological evolution you're never going to trace over them from the brain point of view, which is precisely what we would like if you only want to calculate the the black hole contribution to the entanglement entropy. So that's one reason. That's a brain world reason. And the second reason is that you can look at this picture again, this funnel picture here. Let me go up. Sheesh. Yeah. Yeah. So this picture here. So the point is that, so if you have an extremal surface in AdS CFT, in the underlying AdS CFT geometry, it is meaningful. It's more meaningful to have an extremal surface that is anchored on the co-moving scale. The reason being that the scale factor is related to the radial direction of the brain, and if you fix the distance in physical distance on the brain, what will happen is that these surfaces basically would shrink as you go to later and later times, because the brain is moving up, and because of which the physical distance on the brain is actually so the physical distance, if it is held fixed in the conformal, in the coordinates where the AdS warp factor has been extracted, these geometries have to shrink. So in a sense, this doesn't really capture. So the underlying AdS CFT extremal surfaces are naturally sensitive to the co-moving extremal surfaces that one computes. So that's the second point. Yeah. So let's come here.
So Chethan, can we end in 2 minutes, 2-3 minutes now?
Yeah, I think so. I think we can end it in 2 minutes. So I think that's essentially the only point that I kind of wanted to emphasize. So the point is that once you do compute the entanglement entropy of a co-moving distance, what happens? So let me skip to this slide. What you find is that the co-moving entanglement entropy comes with a natural UV cutoff, because the brain world calculations are naturally UV finite. There is no divergence in them. So what that means is that the quantities that you're computing automatically have like entanglement, which is the time dependence of these things is automatically removed. So so there is a natural way in which one can argue that those dependencies precisely cancel the time dependence coming from the moving of the brain. So that's essentially the only point. And if you believe that, then I think the calculation just goes through as before in the case of the fixed AdS geometries. And this is basically that's kind of the punchline in some sense. So that gives you a strong suggestion that the cosmological islands resolve a version of the information paradox for these eternal cosmological black holes, because they're critical, and because they're critical brain worlds, the gravitons in them are massless. So you find that this is so this is a context where there is islands, and the island physics seems like it is relevant for solving the information paradox. And you have so you have a counterexample, or so to speak, for the massive gravitons are required for this kind of a setup. Okay, I think I'll just flash these slides, and I think I can stop here. So sorry, the slides were a little too much, and it's 60 slides too much here. Hopefully, but the message was clear. I kind of tried to skip through the whole thing.
Thanks, Chethan. It was a great talk.
Thank you.
Yeah. So we have some time for discussion now. Maybe five minutes or so we can have. So any questions from the audience? Whoever is left now. Okay, then I can ask something to Chethan. So in all these computations of this QES, it's quite clear that it's very complicated calculation, but somehow the claim is that you can easily extract the Hayden-Preskel time, because it's essentially the location of the quantum extremal surface is capturing the Hayden-Preskel
so there is
time.
The Hayden-Preskel time is better formulated for the evaporating black hole, right? So here what I'm talking about, these islands are actually outside the horizon,
right?
So there is
but still it is some kind of it doesn't matter, right? I mean,
I think there should be how much it is outside the horizon. I think it is related to some version of a Hayden-Preskel like argument for the eternal black hole, but I'm not very sure that has been formulated, but it might be my ignorance.
I see.
For the eternal black hole, I don't think it has really been formulated, but Hayden-Preskel is usually formulated in terms of you throw in some diaries into the black hole and then wait for the Hawking radiation to come out and so on and so forth. But I suspect very strongly that there should be an analogous calculation here as well.
So, there should be something, some kind of similar kind of time scale which one can extract.
So, you're absolutely right that the time scale involved is somehow very similar to the Hayden-Preskel type of time scale. It's just that for eternal black holes, these islands are outside the horizon.
I see. So somehow the claim is that this should be very easy to kind of extract, although the other part of the computation details is. So maybe
it's easy to estimate in the sense that it is kind of related to the scrambling time, basically.
Exactly. So,
So you have this. But that's an estimate that you can estimate, and I think that so that you can do.
And basically what they do in these computations is that they look at very late time, and they can extract the late time behavior of the extremal surface.
Right.
And somehow they could extract this. So it will be nice if in your setup you can do something like that.
Yeah, I think that the question here would be that it will be something like I guess it will be something like so the point is that the theory. So what is the on the brane world? We are just saying that the theory is it will be related to the central charge and stuff like that. So if you have the S black hole and the central charge, then you can compute it. So, and I think that is, I don't think it will be any different from the standard expressions that I can't remember exactly what it is, but I don't think it will be any different from the standard ones.
Essentially related to log of the entropy.
Yeah. So I think there is an SBH by C or something like that is there, but yeah.
Yeah, except that here perhaps there is some time dilation issue, perhaps, or something.
So the note that the entanglement entropy that I'm talking about is always the co-moving entanglement entropy. So somehow that part has already been taken out. So once you do the co-moving entanglement entropy calculation, the claim is that the thing that you get is exactly the same, or the structure is exactly the same as what you expected in your AdS brane worlds. So if you look at the full entanglement entropy, and that it's not very clear how to formulate that question, by the way, because your fixed entropy. So note that, for instance, if the horizon is expanding, if you wait long enough, the horizon will come and hit your asymptotic, wherever you're holding your physical thing. If it is fixed distance, the horizon is expanding, at some finite time it will come and hit you. So it is, in many ways, it is very natural to have the co-moving entanglement entropy. And I kind of looked around a bit. I don't think people have really looked at it, but it just fits very perfectly with this thing. So I think it is partly because people have not looked at brane world entanglement entropy. And I think what is also interesting is that on the brane world, the entanglement entropies are automatically finite. So which means that the question of what cutoff are you looking at is implicit in the brane world itself. And the claim is that a co-moving cutoff is the natural one if you have a time independent entanglement entropy. That's the claim. So, and that also kind of nicely fits in with that. Yeah, the last part was, I had to kind of rush through it, but I think that kind of is, it somehow many things kind of fit together. So, yeah.
Okay, so now there's a small, we can have a small discussion on this, on kind of questions Suresh was asking.
Mm-hmm.
So, and you were also referring to in the very beginning. So
Mm-hmm.
I think one of the interesting challenges, of course, as you're saying, this page curve is not addressing how you're actually restoring the mechanism through which you're restoring the unitarity.
Right.
That's probably because I think we don't understand the emergence of semi-classical black hole itself, because it's supposed to be some kind of
Right.
averaging
Yeah.
over some microstates. And
yeah. So it's somehow, so the way in which one should think about it, I think, is at least the way in which I've heard people talk about it, is that what you do is you think of this, you know, instead of, so the original page calculation had entanglement entropy, and you looked at the entanglement entropy directly of some system which had, you know, two tensor factors, one subsystem and the rest. So, and you just looked at directly at the entanglement entropy of the system as a Hilbert space and all that. But instead, what we have done here is that you have looked at this a Euclidean path integral definition for the entanglement entropy, and that you use as the definition of the entanglement entropy. So if you use a Euclidean path integral to define an entanglement entropy and allow this replica wormholes or whatever, so then you automatically get the entanglement entropy that has this page curve like behavior. So, but why is it that you're replacing the actual entanglement entropy with a Euclidean path integral definition of entanglement entropy? Is so that's where this, you know, I don't know whether you've looked at it in any detail. So the question of whether the gravity, you know, semi-classical gravity should be understood with an ensemble and so on and so forth. People will say various things like that. Yeah, but I think it is still up for.
Yes, but still, what one would like to believe that the scale of non-locality will be e to the power minus s or something like that. That should be this.
But the scale of non-locality here, you know, at late times is very large, right? Because that's why you have islands. Islands are like it's an extreme form of non-locality in some sense. Because the radiation that went away long ago is the thing that is actually. So it's saying that the interior of the black hole is in the entanglement edge of the old radiation. That's the statement.
Yeah, but somehow that is the nature of the observable that you're computing. Perhaps it's not in the. I mean, one can still do semi-classical. Whether one can trust semi-classical calculations, that's the question. And here, what the page curve actually is trying to tell you is that how, you know, you need some calculations which are not e to the power minus s type, which are like, you know, which actually are secular and it is polynomial in the entropy or
yeah. So I think there are two questions here. One is that, you know, one thing that you would like to, so to really fully resolve the information paradox, or at least the, you know, the page curve version of the information paradox, is that you would want, or even more generally maybe, is that what you would like to have is you would like to get the state or the, you know, the density matrix of the final, you know, once the black hole is radiated away, what is the final state? This is what you would really like to have. So that is basically an exponentially large number of, you know, matrix elements. That's one way in which I think I heard Douglas Stanford or somebody saying something of the kind in the strings conference. And that's like, I think that's a natural way to look at it, which is that you have you know, an exponentially large number of, you know, and density matrix is basically a huge number of data, matrix elements. So, but instead, what the entanglement entropy, or even if you compute the Renyi entropy, what it computes is basically an order n number of quantities. Those quantities, semi-classical gravity knows. That's what is surprising in some sense.
Exactly.
So semi-classical gravity can compute it, but those order n number of quantities, gravity can compute. But on the other hand, if you really want to know the full state of the final system, I think you need some UV complete setup.
Exactly. That's a surprising thing that you can capture this non-locality through the semi-classical geometry itself. I mean, in some way that is the islands. So I don't think you would agree that it's not fully understood, right? I mean, what exactly is going on?
I definitely agree. Yeah, it's not fully understood. But what I would say is that I think that the fact that the page curve can be reproduced, I think it is very suggestive. I think it is not nothing, because it is there is something to be understood here. And yeah, so I think that this final thing that I said, which is that semi-classical gravity, maybe it should be understood in terms of an ensemble average or something like that. And if you, so any element in the ensemble would actually reproduce the page curve, but because you're doing the ensemble average at the end of the calculation, you basically end up finding the page curve anyway, even though gravity is, you know, semi-classical gravity is an ensemble average. So that's the way in which I would probably think about it at the moment. Yeah.
Okay. So thanks again for the nice discussions and the nice talk that you gave.
Thank you.
And
Sorry,
we enjoyed it very much.
So
no, it is fine. It was.
I just made the slides yesterday, and I did not know how to compress it. I didn't have enough time to. I would have cut it short a bit more if I had like a little bit more time. Sorry.
Okay, no problem.
Trial run of the talk.
Thank you, Chethan.
Thank you, Chethan. And see you next time for Suresh's talk, all of you.
Yeah.
Bye.
Okay.
Bye.
So sign off.
Yes.
All right.